Okay, let's do some basics before we get to the specifics. All right, just want to say this. As we use it, it'll sink in. So just watch it and then let's get into it. Vectors 3. I want to talk about coordinates and angles. And then I want to talk about basic trigonometry. You might be familiar with it, but I'm going to show you some things you got to be kind of real quick with. Pythagorean theorem, definition of sine, cosine, and tangent. And then the arctangent, or the inverse tangent. These are the same thing. Or you could write it as tangent to the -1, which is a horrible notation, except that it's really fast to write it. So it's confusing. These give you an angle. This is a way to get an angle. So you know x to the -1, that means 1 over x. However, tangent to the -1 of something is not 1 over tangent. So how do we do 1 over tangent? If you want 1 over tangent, this is really bad notation, but it's what we use. You have to do the tangent of something to the -1. That's 1 over tangent. How bad is it? Sine squared of an angle, let me write that clearly, sine squared of an angle is equal to sine of the angle times sine of the angle. So I put the exponent there. That's also the same as sine of the angle squared. But if that's -1, then that's all of a sudden the inverse or the arc of that thing. So horrible notation, just make sure you're clear on that. Anyway, let's talk about this. Let's first do coordinates here. Just a few little notes, and you'll see, again, we'll use this a lot throughout physics. Coordinates, you get to choose coordinates. Choose wisely. If you do, you get to simplify your analysis. In this case, usually we're talking about simplifying the algebra. There are lots of coordinate systems. There's polar coordinates, spherical coordinates, cylindrical coordinates, not in this course, but they do make things easier. You got to pay up front. You got to set it up a little bit, and that's the confusing part, but then you get the payoff with the easier analysis. So for us, usually that means that we'll choose whatever direction the acceleration is in, that's going to be one direction. Call it x, call it y, we'll see. Then the perpendicular direction, the other direction, and it's key to realize that these two are perpendicular, independent motions, independent directions. So we'll choose one direction and then another, however you want. You can tilt them, you can do whatever, but they've got to be perpendicular, independent. Okay. So for one drawing we might make is a side view of a process. So what I've drawn here is I put my ground here, put the ground there, and we can have lots of things happening, and we're going to in this course. No matter how we choose our coordinates, vertical will be up or vertical down, horizontal one way or horizontal the other way. And that's level, of course. Now, if you throw a ball, well, that ball is moving up and down while it moves over. So in that case, we've got an acceleration in the y direction of negative, because it's down, g, free flight acceleration. And as it goes to the side, we're going to see soon, the acceleration is 0. So that's a great coordinate system for throwing things in the air. And it's often a good example. And you can see that this is a side view watching something fly like that. Now you can also do a side view where you can slide something along an inclined track or surface. Inclined surfaces are good examples, and they're more useful than you might think. If you think about anything that's a threaded ramp, you've got a screw that goes up and down, and those are very useful tools for mechanical advantage and things. So it's a good example, and you'll notice that whether you're going up or down, the acceleration is going to be along the surface. It's not going to jump off the surface. So the acceleration perpendicular to the surface is 0, and all the acceleration is going to be along that direction. So this is a much better choice than vertical and horizontal for this process. So we'll see that later. And this is an example that's kind of neat. It's a car driving around a banked surface. So imagine that the road is inclined as you go around a curve, and you'll find later that in fact all the acceleration is this way, AX, and it's the speed squared over R. Don't worry about that, and that the acceleration in the y direction is 0. Again, it's kind of nice, and you'll see why it's nice later. Don't overprocess this. So that's ways of choosing coordinates in side views. And we'll have to track down angles. A top view, keep in mind that if I'm looking down on the ground and I'm watching ants crawl on the ground, or spiders, or snakes, whatever you don't like, it stirs your imagination. Or if I'm looking down from a helicopter on a road, a flat road, and cars are driving, that all my directions on my picture, even though I've drawn it here on the board, vertical and horizontal on the board, you take that flat on the paper, it's all horizontal, and in fact, all these are horizontal directions. A common way to deal with that, and it doesn't have to be the only way, is to talk about north, south, east, and west. So that's just a pretty common convention if you're talking about, say, driving or boating or whatever it is. Remember, north is not up. You can't go to Canada that way. Good luck, right? You're not going to get there. So north is horizontal. These are horizontal directions that you need your compass to point to. A couple of things I want to point out here. One is, the terminology is a little odd, but it makes sense once you get used to it. Let's see, if I were to be traveling or directed, have a vector directed, any of those vectors, northeast, I could use that roughly saying, it's in this first quadrant. Strictly speaking, northeast is 45 degrees. That way. Strictly speaking, northwest would be 45 degrees that way. Roughly speaking, somewhere in there. Strictly speaking, southwest is 45 degrees between south and west. And then, of course, this would be what? Southeast, strictly speaking. So you have to say for being looser. Now, if I want particular direction, I can look at the angles. We're going to have to specify direction by angles. Okay. Here, in the side view, I could talk about the angle. For example, here's a ball that's flying through the air at that moment. It's got a velocity v2. I could talk about the angle that it makes up from the horizontal, or I could talk about the angle it makes down from the vertical. Since these axes are perpendicular, orthogonal, then if this is 28 degrees, then what's this? 62 degrees, right? Either one's fine, as long as you say, you can't just say 28 degrees, you've got to say from where. 28 degrees up from horizontal, 28 degrees down from horizontal, right? And usually we choose the angle from horizontal in a side view. Okay, but you know, you just have to specify it and you'll see in problems how you do that. This top view thing, when we're using north, east, south, west, what we do is as follows. We talk about an angle, like if I have something out here, then this angle would be heading north from east. Right? So there I could say, let's say it's 20 degrees north from east. And this word of, in a sense, really means from. So if someone said 20 degrees north of east, I start east, then I rotate 20 degrees, which way? towards north. 20 degrees north from east, not 20 degrees north from west, 20 degrees north of or from east is the language we use. It's a little confusing, I know. Now that's the same, so if you said walk 20 degrees north of east, you'd walk that way. If you said walk 70 degrees what? Well, you're walking towards east from north. So that would be walk 70 degrees east from or of north. They're the same direction. You can specify it either way. One isn't more correct than the other. And if someone tells you that, you start at north, head east, 70 degrees. And read it backwards. Here you start, head east, rotate towards north, 20 degrees, head on out. Okay? So similarly, if I wanted to go out over here, I could specify that direction either going here, which would be some angle heading west from north, so that would be west of north, some amount. Or I could say the same direction, saying I'm going some degrees northward from or of west. Confusing, sort of, but just think of it reading backwards. From west, I head north this many degrees. So this would be southward from or of west. That would be south of west. This would be west of south. Hopefully you get that. And then we can go over here. That would be southward from or of south of east. Or I could give the angle heading east of south. So let's just take a look at that kind of quickly. Two little points here. One is, if I gave you 20 degrees west of south, can you visualize it? South, here's west, so I'm going to head out 20 degrees there. That's equivalent to the complementary angle, 70 degrees, and I just flip these guys, going south from or of west. Whatever. 20 degrees west of south is the same as 70 degrees south of west. You can see it. A little bit of a brain twister, get used to it, it's fine. One last point on these coordinates, and we'll get into using them, this is again just preparatory stuff, but when you've got a coordinate system, you can move that. When you're making a coordinate system, you're kind of making a grid. So let's go ahead and use it doesn't matter if we use vertical, horizontal, or north, east, south, west. But if I have a vector over here, and it's heading, say, this direction, let's make it, I can head back this way. Well, what I do is I take my coordinates, and let's color code them. And I place that through the tail. So this is east, that's eastward, and through the tip. Now, if this is north, and that's south, I can put that through the tail. There's north, and there's north. And so I can see that this vector is pointing west and south. So you can move that coordinate. The coordinate is really a grid that goes like this on your whole piece of paper. And you just move it over to your particular vector, and then you're making graph paper. Okay, cool. So that's that. Hopefully that's clear. Not talking to me. The other basics are, and you probably know this, but you need to know this fast. That needs to be no hesitation. And sometimes we have little holes. We've been doing lots of things, so it's time to clean up the holes. Basic trigonometry. This is really fun. We should have all used rulers and measured triangles and gone out there and just measured these lengths and see how they're related. And Pythagoras certainly did over 2,000 years ago. And what do we know? So we're looking at right triangles because it's useful. Again, our coordinates are perpendicular, so this is going to be very useful. We've got a hypotenuse, the longest side, which is opposite the 90-degree or pi over 2 radian angle. Then I've labeled this angle alpha, and the side opposite alpha is A. Then I've labeled this angle beta, and the side angle opposite beta is B. It doesn't matter what you call them, I just did that here as an illustration. So you know Pythagorean theorem. The longest side, if you measured that length, would be equal to one of the short sides squared plus the other short side squared, square root. And it works. Now you should, here's another little level, you should realize that then a short side is equal to the longest side, hypotenuse squared, minus the other short side squared, square root. A is equal to that, B is equal to that. And just, it's like, oh yeah, I never really noticed that. Boom, but you can write that down very fast, that's good. Fine. So that's how you relate the lengths. What about the lengths to the angles? Well, they figured out that it turns out that the ratios of the lengths are always the same if you have the same angle. Which is to say, if you made this a bigger triangle with the exact same angles, then that side capital B and this side capital A, and maybe this hypotenuse capital H, the ratios of those lengths stays the same if the angles that stay the same. That is, they're a function of the angle. And so they made up these, I don't know, rather confusing names, right? Sine and cosine and tangent. But, you may know of the memory aid, SOHCAHTOA. Some people say Chief SOHCAHTOA. It's a memory aid. What does that mean? It means that the sine of an angle is equal to the side opposite that angle divided by the hypotenuse. Sine of alpha is equal to the side opposite alpha divided by the hypotenuse. The side opposite alpha is A, or capital A, doesn't matter, over the hypotenuse. And so you literally could measure this, and sine is a fraction. Which side's longer? H. So that's less than 1. Cosine, complementary sine, of alpha is the side adjacent to alpha. What's next to alpha? B. Yes, H is, but that's the hypotenuse. So the short side adjacent to alpha is B divided by H. Again, H is longer, so these guys are less than 1. Important. They're fractions. They're just fractions. Okay. Tangent, TOA, is the tangent of an angle is the side opposite that angle divided by the side adjacent. They're just definitions. They're just fractions. That's all they are. So tangent of alpha would be the side opposite alpha, which is A, divided by the side adjacent to alpha, which is B. Now that is unclear. Whether that could be more than 1. A could be longer than B, depending on what angle it's talking about. So this could be more than 1 or less than 1. Right? You've got a full range here. Okay, another thing to notice here. The sine of alpha is A over H. In terms of beta, A is adjacent. So for beta, it's the adjacent over hypotenuse is A over H. And so the complementary sine of the complementary angle is the same. B, in terms of beta, well, it doesn't matter. You can use cosine alpha, you can use sine, it doesn't matter. So notice that. And one final little bit is this. How are we going to use this? The way we're really going to use this, the primary thing is, we could use either one of these. So that, this. Pythagorean theorem. That relates to sides. If I have two sides, I can find the other side length. And the other is, what about the angles? How do I find the angle? Well, we often use tangent, and we use that silly little notation, the inverse tangent. I highly recommend the absolute value of the ratio, so that you just get a number and you can look at which direction it is on your picture. The absolute value of A over B. Well, what does that give me? Tangent of alpha is A over B. So if I undo that, the inverse tangent of A over B is alpha. Tangent of beta is B over A. So if I have the length B and the length A, I can either measure with a protractor or calculate it here, and that'll give me beta. It doesn't matter. I mean, if you have alpha, if that's 20 degrees, that's 70 degrees, whatever. So it doesn't matter. But that's how you get the angle using those sides. And finally, what you need to be able to write quickly is A is equal to the short side is equal to the long side times a fraction less than 1. Which one? Well, let's see, that would be the sine of alpha, wouldn't it? Because the sine of alpha is A over H. Or H times the cosine of beta. Check that. Make sure you can write. You shouldn't have to write that fraction anymore. You should straight away just write that. Or B is H times the sine of beta, which is the same as H times the cosine of alpha. So these are the definitions, but you want to kind of move past that and be able to write these things along with Pythagorean theorem, and you're good to go. And now what are you doing? Well, vectors have parts, perpendicular parts. So we can relate the part in one direction and the part in the perpendicular direction to the whole magnitude of the vector. And we can relate the angles, and you're good, you got everything you need to know. Now we'll put it to use in strong fashion.